Hello and welcome to your ultimate guide for the D425 OA, Introduction to Chemistry course. My goal today is simple: give you everything you need to fully understand the key concepts, master them, and walk into your D425 OA exam with total confidence. In this video we'll cover chemical bonding, ionic compounds, covalent geometry, mole concept, reactions stoichiometry. With over 100 plus success stories, we have proven our videos will help you pass your exam on the first attempt. And remember, our website offers free exam guides and practice questions to help you ace your D425 OA exam. You'll find the link in the description below, so be sure to check it out and get the resources you need to study smarter, not harder. So let's get started.
So why do atoms bond at all? The answer is beautifully simple. Atoms bond because bonding lowers their energy and makes them more stable. The benchmark for stability is a full outer shell of electrons, just like the noble gases have. We call this the octet rule because a full shell usually holds 8 electrons. There are two main ways an atom reaches that stable octet, defining the two great families of bonding. The first is to transfer electrons completely, which happens between a metal and a non-metal, giving an ionic bond. The second is to share electrons, which happens between two non-metals, giving a covalent bond. Here is a quick way to predict which type you have. We look at the difference in electronegativity between the two atoms, which measures how strongly each one pulls on shared electrons. A small difference means the electrons are shared evenly, a non-polar bond. A larger difference makes it polar, and a very large difference makes it ionic. Picture a familiar example: table salt. A sodium atom has one outer electron it would love to lose. A chlorine atom is one electron short of a full shell, so sodium hands its electron to chlorine. Now, sodium is a positive ion, chlorine a negative ion, and their opposite charges snap together. On your assessment, one very common question asks you to identify the bond type. Here is the trick that never fails. Look closely at the elements involved. If a metal is joined with a non-metal, the bond is ionic. If two non-metals are together, it is covalent. That one check answers the question instantly. To lock this in, remember a short phrase. Metals are givers, while non-metals are takers or sharers. A giver and a taker create ions that attract, which is ionic. Two sharers split the difference, which is covalent. Picture sodium giving away its electron, while two non-metals insist on sharing. That image carries you far. What we just covered is exactly the material you will find in our free practice question bank. These are not just basic definition questions either. They are designed to test your deep understanding, just like your real assessment will. Working through them now turns these ideas into instincts you can rely on under pressure. Let us go deeper into ionic bonding, our first major type. When a metal meets a non-metal, the metal loses electrons to become a positive ion called a cation, and the non-metal gains them to become a negative ion called an anion. These opposite charges attract in every direction, building a three-dimensional crystal lattice. Wonderfully, the periodic table predicts ion charges for you. Elements in the first column form a charge of positive 1. The second column forms positive 2. Aluminum forms positive 3. On the other side, the oxygen family gains 2 electrons for a negative 2, and the halogens gain 1 for a negative 1. Transition metals are a little trickier because many can form more than one charge. Iron, for example, can be iron 2 or iron 3. To show which one we mean, we write a Roman numeral right in the name. So iron 2 means the ion carrying a positive 2 charge, while iron 3 carries a positive 3. Next come polyatomic ions, which are small groups of atoms bonded together that carry one overall charge and act as a single unit. You must memorize these because they appear everywhere. Some essential ones are ammonium, hydroxide, nitrate, sulfate, carbonate, and phosphate. Make flashcards on day 1 because they are the alphabet of this section. Many polyatomic ions come in families that differ only by how many oxygens they hold. Take chlorine as the model. The base ion ending in 8 has a set number of oxygens. The ending 8 has 1 fewer. The prefix per gives 1 more, while hypo gives 1 fewer still. The charge never changes. To write an ionic formula, remember the compound must be electrically neutral. So positive and negative charges balance perfectly. The shortcut is the crisscross method. You take the size of each ion's charge and drop it down as the subscript of the other ion. Always reduce to the simplest whole number ratio at the end. Naming ionic compounds follows a clean, predictable pattern. You name the positive ion first using the element's name, add in a Roman numeral only if it is a variable metal, then name the negative ion, changing its ending to ID for a single element. One crucial rule: never use Greek prefixes like dia or tri in ionic names. Acids deserve attention because their naming has its own logic. A binary acid made of hydrogen and one other element takes the form hydro, then the root, then oxy acid. An oxy acid, which contains oxygen, drops the hydro. If the ion ends in 8, the acid ends in ik. If it ends in et, the acid ends in OS. Ionic compounds share a signature set of properties worth knowing. They have high melting and boiling points because the lattice is held by strong attractions. They are hard yet brittle, shattering when struck. And here is a favorite exam point. They conduct electricity only when melted or dissolved, never as a solid, because the ions must move. Here is the exam insight that ties ionic naming together. Whenever you see a metal in the formula, switch into ionic mode immediately, meaning Roman numerals and no prefixes. Calcium chloride is simply calcium chloride, never calcium dichloride. Students lose easy points by adding prefixes here. So let that be one mistake you never make. I know we are covering a lot of detail, and you might wonder how to practice applying all of it. That is precisely why I put together those free practice questions I mentioned earlier. They let you work through problems that combine naming, charges, and formulas exactly the way your assessment loves to blend concepts together. Now we shift to covalent bonding, where two nonmetals share electrons instead of transferring them. Because both atoms pull strongly, neither one gives electrons up, so they share to complete their octets. Bonds can be single, sharing 1 pair, double, sharing 2 pairs, or triple, sharing 3 pairs. With each step, the bond grows shorter and stronger. Naming these molecular compounds is where Greek prefixes finally come into play, the big contrast with ionic naming. The prefixes tell you how many of each atom are present. 1 is mono, 2 is di, 3 is tri, 4 is tetra, and so on upward. The second element always takes a prefix and ends in YDE. A Lewis structure is a simple drawing showing where all the valence electrons sit, which atoms are bonded, and where the lone pairs rest. It is the blueprint for a molecule's shape and behavior. The very first step is always to count the total valence electrons, adding up the outer electrons of every atom. After counting, you choose a central atom, usually the least electronegative one, and never hydrogen, which makes only one bond. You connect the outer atoms with single bonds, then spread the remaining electrons as lone pairs to complete each octet. If the center still lacks 8, pull in lone pairs to form double or triple bonds. Consider water as a quick example. Oxygen sits in the center with 2 hydrogens attached, leaving 2 lone pairs resting on the oxygen. Now picture carbon dioxide. Carbon sits between 2 oxygens, but single bonds leave carbon short. So each oxygen forms a double bond to carbon. Both atoms then reach a full satisfied octet. A molecule can sometimes be drawn correctly in two or more equally valid ways that differ only in where a double bond sits. The real structure is then an average of them all, which we call a resonance hybrid. Ozone is the classic case, where the true molecule blends both drawings into one smooth, even reality. Formal charge is a bookkeeping tool that helps you pick the best Lewis structure when several seem possible. It is the charge an atom would carry if every bonding pair was split perfectly evenly. The best structure keeps formal charges as close to zero as possible, with any negative charge sitting on the most electronegative atom. Now for one of the most rewarding topics, predicting molecular shape from one simple idea. Electron groups around the central atom repel each other and spread out as far apart as possible. You count the groups where each bond or each lone pair counts as one group, and the molecular shape follows directly. Here is a pattern examiners adore. Methane, ammonia, and water all have 4 electron groups around the center, yet their shapes differ. Methane has no lone pairs, forming a symmetric shape called tetrahedral. Ammonia has 1 lone pair, giving a trigonal pyramid. Water has 2 lone pairs, bending further, and each pair squeezes the angle smaller. Let us talk about polarity, starting with a single bond. A bond is polar when the 2 atoms differ in electronegativity. So one end pulls the shared electrons closer and turns slightly negative, while the other turns slightly positive. This tiny separation of charge is called a dipole, pictured as an arrow pointing toward the greedier atom. Here is the part most students miss. A molecule can have polar bonds and still be nonpolar overall if its shape is symmetric, so the dipoles cancel. Carbon dioxide is the perfect example, perfectly straight, so its 2 poles cancel exactly. Water, being bent, cannot cancel, so it stays polar. Symmetry kills polarity, asymmetry creates it. Finally, intermolecular forces are the attractions between separate molecules, and they control properties like boiling point. The weakest, present in everything, are London dispersion forces. Stronger are dipole forces between polar molecules. Strongest is hydrogen bonding, which appears only when hydrogen is bonded directly to nitrogen, oxygen, or fluorine, and it explains much of water's behavior. For the exam, keep 2 ideas crystal clear. First, to judge molecular polarity, check both whether the bonds are polar and whether the overall shape is symmetric. Second, never confuse the forces between molecules with the bonds inside them. Boiling water breaks the weak attractions between water molecules, not the strong bonds within each one. If some of these advanced concepts feel challenging right now, please do not worry. That is completely normal and exactly why I created that comprehensive practice question bank. Working steadily through those problems will solidify your understanding of shapes, polarity, and forces, and build the quiet confidence you need walking into your assessment. Now we reach the mole, the most important counting idea in all of chemistry. A mole is a specific number of particles, just like a dozen always means 12. 1 mole contains about 6.022 times 10 to the 23rd particles, a value we call Avogadro's number. It bridges atoms and grams. Converting between moles and particles is straightforward once you see it. To go from moles to particles, you multiply by Avogadro's number. To go the other way, from particles back to moles, you divide by that same number. Just remember that 1 mole of any substance contains that enormous count of molecules, atoms, or formula units. Molar mass is the mass of 1 mole of a substance, measured in grams per mole. Here is the elegant connection. The molar mass of an element in grams equals its atomic mass straight from the periodic table. For a compound, you simply add up the molar masses of every atom in the formula to find it. Molar mass is also your conversion factor between grams and moles, the two quantities you actually weigh and use. To find moles, divide the mass in grams by the molar mass. To find mass, multiply the moles by the molar mass. This single relationship unlocks an enormous fraction of the calculations you will face. Picture a simple map with moles always sitting in the middle. On one side is mass in grams, reached by using molar mass. On the other side are particles, reached by using Avogadro's number. To travel from grams all the way to particles, you must always pass through moles in the center. There are no shortcuts. Percent composition tells you what fraction of a compound's mass comes from each element. For any element, you take the total mass contributed by that element, divide by the molar mass of the whole compound, and turn it into a percentage. This is how a fertilizer label tells you exactly how much nitrogen you're buying. Two kinds of formula round out this lesson. The empirical formula gives the simplest whole number ratio of atoms, while the molecular formula gives the actual count in one molecule. The recipe for an empirical formula is a chant worth memorizing. Percent to mass, mass to moles, divide by the smallest, multiply until whole. When mole problems appear on your assessment, the smartest first move is to convert to moles before anything else. Moles are the universal currency every other quantity passes through. Write out your map, mark where you're starting and where you need to land, and let each conversion factor guide you one step at a time. Remember that mastering these concepts takes practice and genuine application. The free practice questions are designed to help you take what you're learning here and turn it into real exam-ready skills. They walk you through mole conversions and composition problems again and again until the steps feel natural and automatic rather than intimidating. Now let us bring atoms together and watch them react. A chemical equation is a symbolic recipe. The starting materials, called reactants, sit on the left and the products they form sit on the right, with an arrow meaning yields. We add small state symbols showing whether each substance is a solid, liquid, gas, or dissolved in water. Because matter cannot be created or destroyed, every equation must be balanced, meaning the same number of each kind of atom appears on both sides. We balance by adjusting only the big numbers in front, called coefficients. You must never change the small subscripts inside a formula because that would turn the substance into something completely different. A reliable balancing routine helps enormously. Count the atoms of each element on both sides. Balance metals and polyatomic ions first, saving hydrogen and oxygen for last. Adjust one coefficient, then recount before moving on. When a polyatomic ion appears unchanged on both sides, treat it as a single unit rather than breaking it apart. Most reactions fall into a handful of recognizable types. In synthesis, simple pieces combine into one product. In decomposition, one compound breaks apart. In single replacement, a lone element kicks out another from its compound. In double replacement, two compounds swap partners. Combustion burns a fuel and oxygen, and neutralization joins an acid and base into water. Many reactions also involve a transfer of electrons, which we call reduction and oxidation, or redox. The simplest way to remember the directions is the phrase oil rig. Oil means oxidation is loss of electrons. Rig means reduction is gain. The atom that loses electrons is oxidized, while the atom that gains them is reduced. When two dissolved solutions mix, a solid called a precipitate may suddenly form, and solubility rules predict whether it will. Here is your anchor that makes these problems far easier. Anything paired with a nitrate with a first column metal or with ammonium stays dissolved every time. Those three are your reliable, always soluble friends. When a precipitate does form, the clearest way to show the real chemistry is a net ionic equation. We split every dissolved compound into its separate ions, then cancel the ones appearing unchanged on both sides, which we call spectator ions. What remains shows only the ions that actually combine into the new solid. Simple and honest. The biggest reaction trap on the exam is changing a subscript while balancing. Promise yourself you will only ever touch the coefficients out front. A second common trap is misclassifying reactions, so study the patterns until you can spot each type at a glance. Recognizing the type often lets you predict the products before calculating anything. As we move into our final major topic, remember that understanding these concepts is only the first step. The real mastery comes from applying them, which is where those free practice questions become invaluable. They are completely free, designed specifically for your assessment and waiting for you at the link in the description below this video. Stoichiometry is the math of chemical reactions and the grand payoff of everything we have built today. The coefficients in a balanced equation give you a mole ratio, telling you the exact proportions in which substances react and form. From those numbers, you can build conversion factors connecting any two substances. Real lab amounts come in grams, but mole ratios only work in moles, so every mass to mass problem follows one path. Convert grams of your starting substance into moles. Apply the mole ratio to find moles of your target. Then convert those moles back into grams. Grams to moles to ratio to moles to grams. In real reactions, the ingredients are rarely present in perfect proportions, so one of them runs out first. That one is the limiting reactant because it limits how much product can form. The other is left over in excess. Think of building cars where running out of wheels stops production, even if plenty of bodies remain. Three kinds of yield finish our story. Theoretical yield is the maximum product possible, always calculated from the limiting reactant. Actual yield is what you really collect in the lab, which is always somewhat less. Percent yield then measures efficiency, found by dividing the actual amount by the theoretical amount and turning it into a percentage. For stoichiometry questions, two reminders will protect your points. Always base the theoretical yield on the limiting reactant, never on the one sitting in excess, and never apply a mole ratio directly to grams. Travel through moles first, every time. Trust the path, work patiently, and these problems become almost mechanical in their reliability. Let us bring it all together now. We began by seeing that atoms bond to reach a stable octet, either by transferring electrons in ionic bonds or sharing them in covalent bonds. We learned to name compounds and acids, to draw Lewis structures, and to predict molecular shapes and polarity from the idea of electron groups repelling. From there we built the mighty mole, our bridge between atoms and grams, and used it for molar, mass, percent composition, and formulas. We wrote and balanced equations, classified reactions, and predicted precipitates. Finally, stoichiometry tied everything into one powerful skill, letting us predict how much product a reaction yields from any starting amount. Notice how every topic connected to the others. Bonding explained formulas, formulas fed into equations, and equations powered stoichiometry. Chemistry is not a pile of separate facts to memorize. It is one connected story about atoms seeking stability. If you can see those connections, you are already thinking like a chemist, far more prepared than you realize. Do not forget to grab those free practice questions from the link in the description below. With the deep understanding you gained today, combined with steady practice from those questions, you will walk into your assessment genuinely prepared and calm. They are completely free, so there is nothing to lose and everything to gain. So here is my final encouragement. Review this material, drill those practice questions, and trust the steady work you are putting in. Every expert chemist once sat exactly where you are sitting now. You have the tools, you have the roadmap, and you absolutely have what it takes. Go now and earn that passing score.